Hello friends, in today's video, let us learn about energy released in fission. We know nuclear fission is a process involving large amount of energy and a very huge amount of energy is released in a fission process. So we know in a nuclear fission, a large nuclei is splitted into two smaller ones, and often the mass of the final products is lesser than the mass of the initial nuclei. So some mass is getting lost in the process of this nuclear fission, and this difference in mass is actually getting converted into energy according to the Einstein's relation E equal to delta mc square. The lost mass in the nuclear fission is converted into huge amount of energy. Now let us calculate the energy released for in the case of a uranium-235 nucleus. So consider a uranium-235 nucleus. We know the uranium-235 will undergo a nuclear fission when it is bombarded with a neutron, which is 0 and 1. It will be converted into 236 uranium, 92 uranium-236, which will later split into other particles, fission fragments. So in this process of calculating the energy, we will use two methods to find the energy liberated. So in the first method, let us use the binding energy per nucleon to calculate the the energy released in a fission process. So we have already studied the binding energy per nucleon curve, and from this curve it is clear that for a uranium nucleus which has a mass number of around 236, the binding energy per nucleon corresponding to this mass number is approximately 7.6 mega electron volt. And this uranium nucleus having 7.6 mega electron volt binding energy per nucleon is getting splitted up into smaller fragments which has higher binding energy per nucleon. So the fission fragments will have a binding energy in the range of 8.5 mega electron volt. So we know the initial nucleus, which is the uranium, has a binding energy of 7.5 mega electron volt, 7.6 mega electron volt at this value, and the products has a binding energy per nucleon which is equal to 8.5 mega electron volt, MeV. So per each nucleon there is a difference in binding energy of 8.5 minus 7.6. How many number of nucleons are there? 236 nucleons are involved in this fission process, and hence the total energy released will be, energy in this fission process will be total number of nucleons into difference in binding energy per nucleon, which is 8.5 minus 7.6 MeV. So this can be calculated to be equal to 212 mega electron volt approximately. So when a uranium nucleus is undergoing fission, 212 mega electron volt of energy is released. So this is the first method of calculating the energy released in fission process based on the binding energy per nucleon. In the second method, we will use the concept of difference in mass or mass defect in the fission process in order to find the energy released. So in the method 2, let us consider the fission of uranium as indicated in the following equation. When a neutron is added into a uranium, we will get fission fragments And let us consider one particular fission fragment, 42 molybdenum 98 plus 34 xenon 136. Plus 2 neutrons. In this process, let us calculate the total mass of nuclei before fission. So before fission we have one neutron and one uranium nucleus, and so the total mass of this initial particles are, so let us calculate M1 equal to the mass of the neutron, which is 1.0087 AMU, plus the mass of uranium, which is 235, .0439, which is equal to 236.0526 U. So this is the initial mass we have in our hand before fission. After fission, it will be split up into molybdenum, xenon and 2 neutrons. So the total mass we have after fission, let us call it M2. It is 97.906 for molybdenum, then 135.9072 for xenon, then 2 into 1.0087 for 2 neutrons, which is 2.0174 for 2 neutrons, and totally the final mass is 235.8306 U, atomic mass units. So we can clearly see that when the initial particles are converted into the final products, the fission fragments, there is a loss in mass. Mass is getting decreased. So if you calculate the mass difference in mass, it is equal to M1 minus M2. So it will be, so difference in mass is equal to 0.2220 U. And this is the difference in mass when a fission of uranium-235 is happening. So what will be the energy released? Energy release will be mass difference into C square, that is 0.220 into 931.5, that is the conversion of atomic mass unit into mega electron volt, and this will yield you approximately 206.7 mega electron volt. So through this method, in the second method we considered the difference in mass and find the equivalent energy corresponding to that mass defect. We cannot call this mass defect, this is actually difference in mass, and that equivalent energy is the energy released in fission process. So in both the process we get somewhat similar answer. First answer is 212 mega electron volt and the second one is approximately 206.7 mega electron volt. So we can approximately consider that per fission, each fission of uranium-235 nucleus will give us 200 mega electron volt approximately. So very large amount of energy is released in the fission of uranium nucleus. So for future calculations, we can use 200 MeV as the energy per fission of each atom of uranium-235 or each nucleus of uranium-235. Now with this value in our hand, let us also calculate the energy produced by 1 kilogram of uranium during fission. So energy produced by 1 kilogram of uranium-235 due to fission. So we know each atom of uranium-235 when undergoing fission will release an energy 200 MeV. And how many number of atoms are there in 1 kilogram of uranium? We know if we take 235 gram of uranium, then that will correspond to Avogadro number of atoms. Right? That is the definition of Avogadro number. 235 is the mass number or the molecular mass, molar mass of uranium. 235 gram is the molar mass. So 235 gram correspond to Avogadro number. That means 235 into 10 raised to minus 3 kilogram of uranium 235 is equivalent to 6.022 into 10 raised to 23 atoms. So how many number of atoms will be there in 1 kilogram of uranium-235? Bring this factor 235 into 10 raised to minus 3 to the right hand side. So 1 kilogram of uranium-235 will be equivalent to 6.022 into 10 raised to 23 divided by 235 into 10 raised to minus 3 number of atoms. And this much atoms are present in 1 kilogram of uranium. So if each of the atom is undergoing nuclear fission, each atom will produce 200 MeV of energy. So total energy released in the fission of 1 kilogram of uranium is 6.022 into 10 raised to 23 divided by 235 into 10 raised to minus 3 multiplied by, this is the number of atoms in 1 kilogram of uranium, multiplied by 200 MeV, which is the energy released in each fission. You can get a value 5.128 into 10 raised to 26 MeV. So this is a very large value. This much amount of energy is released if 1 kilogram of uranium is undergoing fission. If you convert this value into joule, it is 5.128 into 10 raised to 26 multiplied by 1.6 into 10 raised to minus 13 joule multiplied by 1.6 into 10 raised to minus 13 to convert MeV into joule. And you can also convert this factor into kilowatt hour. So it will be approximately 2.26 into 10 raised to 7 kilowatt hour. So this much amount of energy will be released in the fission process of 1 kilogram of uranium. So a very large amount of energy is released, and this is the reason why nuclear energy is often preferred for electricity production, because a very small quantity of fissile material can bring you a very large amount of electricity. And even for ordinary chemical reactions such as burning of coal or oil, the energy associated is only few electron volt. But in the case of the uranium fission, the energy associated is in the order of mega electron volt, and hence a large amount of energy is released. And this energy released is usually shared as the kinetic energy of the fission fragments. We can obtain the output energy from a fission as the kinetic energy of the fission fragments, and a 20% of the energy is given for beta and gamma rays. A majority of the energy is taken up by the fission fragments as its kinetic energy, and about 20% of the energy is liberated through beta and gamma radiations. And this is the sharing of the energy released from the fission process between the fission fragments and other decays. So I hope you got a broad understanding about the quantity of energy released in fission process. We define the energy released from a fission process. We try to calculate the approximate value of energy released for a uranium-236 nucleus undergoing fission through two methods. First method is the binding energy per nucleon method, and the second method is the difference in mass method, and both yield us a value of 200 MeV per fission of a uranium-235 nucleus. Then we use that value to find the energy produced in 1 kilogram of uranium-235 fission, and that is a very huge value, and that energy is finally obtained as kinetic energy of fission fragments and as the energy released in beta, gamma radiations, etc. So I hope you got a broad understanding about energy released in fission. Thank you.